Hi, this is part 4 of the introduction and grand overview of magnetism. So in this part I'm going to talk about how magnetic fields create forces on moving charges. So far we've covered, other than a general introduction and having talked about permanent magnets, and we've talked about how currents and moving charges create magnetic fields. But let's suppose there is a magnetic field, maybe created by some nearby current, then how does that magnetic field affect a charge that's moving through it? Because remember, fundamentally, magnetism is about interactions between two moving charged particles. So the general law that describes the force, gives us the force, is called the Lorentz force law. And written out in full, it consists of two parts. So the force is equal to the charge times the electric field. That's the part that you know from before. Right? That's electrostatics. That we've practiced to death. The new part, the magnetic part, is this. And this is Q V cross B. So Q is the charge of the particle, like the same as the electric charge that you've plugged in here. V is the velocity of that particle, the force on which we're thinking about. B is the magnetic field the particle is in, and then those two are combined via the vector cross product. So remember, you take two vectors, you take the cross product between them, and it gives you a new vector that's perpendicular to both, and the bigger the angle between those two, the closer it is to 90, the bigger the resulting third vector. For the details and the visualization of the cross product, go back to the previous video where I talk about it, because this cross product also came up in the laws concerning the creation of magnetic fields. Right. But here we assume, okay, some magnetic field is given, some particle of charge Q moves with a velocity v through it, and the direction matters, right? This is not just the speed, the direction is important. And the force is given by this. I could just leave it there, that's it, that's all there is to it. The rest is really exploring the consequences of this. So let's have a look. So here are some examples just to familiarize ourselves with this law, right? The law was Q V cross B. So let me just write this down. Q V cross B. This is as a reminder. Right. Let's take the first example here. I have a magnetic field that's pointing to the right, and I've got a velocity that's sort of pointing to the top right. So remember, for the cross product, we're going to use the right-hand rule. The right-hand rule says your thumb points in the first direction, like the first vector. The second finger, the index finger, points in this direction of the second vector, and the middle finger, if you hold it sort of this perpendicular shape like this, is going to give you the direction of the resulting vector. Let's do this. The velocity is this way. The field is this way, so I have to hold it kind of like this. So then my middle finger, you can't see it, but it has to point down, right? Velocity is up-ish. The magnetic field to the right. The only way my middle finger can point is down. So the force, in this case, would be into the page. Would be down. Right? In general, what you can do is, if you're worried about the angle of V, right, which way I point my thumb, not perpendicular to the direction of the field, that's my index finger, you can always just pretend it's sort of, you just worry about the component of V that's perpendicular to B. That actually works out mathematically because the resulting vector uses the sine of that angle. This is to say, we're really just caring about this component here. V sine of this angle is this. So it's almost like you can ignore the part of the velocity that's parallel to the field. If that sounds a bit confusing, do a couple of examples, and I think you'll see that pattern. Let's do the second example here. So remember, When I've got little dots, it means the field is coming towards us, right? The little trick, little memory trick that I gave, thanks to one of my students of the past, is that you think of it as an arrow, shot from a bow that's coming towards me. I see the point. If it's going away from me, I can see the cross-like tail feathers of it. See, the magnetic field is coming towards us. The velocity is in this direction, like up the page. So velocity, this is coming towards us. Now I'm at an awkward angle here, so the middle finger then has to be perpendicular to those two to that way, right? Velocity, middle finger up, middle finger has to be sticking out over there. That is really hard to show. Like, this would be way easier to show in a classroom. But use your right hand, right? Point your thumb in the direction of the velocity, your index finger in the direction of the field that's straight up. The only way you can make that happen is if you then have your middle finger stick out this way. So the force is, the force is to the right. Force to right. But wait a second. That would be true if this were a positive charge. If positive charge. The right-hand rule gives the direction of a positive charge. I'm multiplying it now by a negative number, so that flips the direction. So here, because the minus sign here, negative charge, force to the left, since negative. Right, so if a negative charge is moving, the minus sign that you get in here, that will flip the direction of the vector. Now here's the third example, where the velocity of the particle is positive again, is straight to the right. The magnetic field is to the left. So they're exactly in opposite directions. Now, how do I make this work? So one thing I said before was that I can really just care about the direction, the component of the velocity that's perpendicular to the B field. In this case, that component is 0. Now the thing you can also use is, remember that this, I could write this also as Q times the speed times the magnitude of the B field times the sine of the angle between them. Let's call it alpha. This would be alpha. Now in this case, the angle between V and B is 180 degrees. Sine of 180 is 0. So there is 0 force. Right? The two ways to see this is the sine of the angle is, in this case, 180. If they were in the same direction, the B field to the right as well as the velocity would also be 0. Or you can think of it in this sort of way here, where you say, I really only care about the velocity, the component of the velocity that's perpendicular to the magnetic field, and in this case that is 0, so that makes the force 0. So there's 0 force. If the velocity is in the same direction as the magnetic field, or just the opposite direction, I get 0 force. Of course, the magnitude, well, that's the easy part in a way. It's the easy part to work out what's the, how strong is the force. The hard part is the directions and turning your hand in awkward ways. Alright, let's keep going. So, one thing not to get confused about, and I mention this because I know it's a common point of confusion, is that you're always asking what's creating the field and on what object is the field creating a force. Often you don't care about one or the other, right? So you're given a problem and it says a particle moves in a magnetic field of strength such and such. And in a way we don't care what caused that magnetic field, we're just asking about its effect. Another problem you might encounter is, I want to create a magnetic field of field strength 5 Teslas, how much a current do I need? So there are questions that are about creation of magnetic fields. And when you encounter a problem, be completely clear what it's asking you, right? So in this video, I'm really talking about what is the effect of magnetic fields that are already there, caused by something else. But, of course, any magnetic field is created by something else. So here's an example where I include both. So take the following. I've got a current, right? and there's a current up in a wire. Now, next to it, there's a negatively charged particle that's right now it's moving up. At this very instant, I take a snapshot and I see, okay, right now the velocity is up. What is the effect of the current? What effect does this current have on that particle? So the way we're going to figure this out, we're first going to find a magnetic field. Okay, it's a current creating a magnetic field. So this is creating our magnetic field. This particle is then affected by the magnetic field. Now, remember from the previous video, we're going to use for a current, we're going to use the curly hand rule. So thumb points in the direction of the current, and then the finger sort of curl in the direction that the magnetic field points. So if I sort of draw it, we draw a separate little drawing down here, with this being the current is up, right? It's sort of like this. It would be like that, and it sort of circles around it like this. Of course, we're going to draw it in 2D here, so the field's going to go into the page on the right of the wire, it comes out of the page on the left of the wire. That still doesn't make sense to you, go back to the previous video. So over here, I'm going to draw it like this. Of course, it gets weaker as I get further apart, so I'm going to go a bit further out. Oops, see, it's already getting wrong. Here it's coming towards us, so I should be drawing dots here. So really I don't care too much what's happening over here, because this particle is sitting on the right hand side. Alright? So this is the B field due to the wire with the current. Notice one thing is the current, right, I, denotes the direction of the positive charges moving up. We're pretending positive charges are moving up. If you have negative charges moving, right, and we know realistically a current in a wire is electrons moving, but they're moving the other way. So if I say the current points up, I mean, physically speaking, electrons are moving down. The magnetic field you're going to get in both those cases is exactly the same, right? Positive charges moving up create the same magnetic field as negative charges moving down. So don't have to worry about this distinction between the electron current, the real physical current, and the conventional current where we pretend positive charges are moving. Right, so we figured out a magnetic field created by the wire. Now we can ask what is its effect. So now we're going to use the right-hand rule for the Lorentz force law. So I've got the velocity is up, like up the page. The magnetic field points down, so it looks sort of like this. How we can see this, right? Like this, and then my middle finger can only stick out to the left. So the force is to the left, except it's a negative charge, so it's going to be to the right. Force, I'm going to make a note, I'm just going to put it sort of like this. Force if charge positive. Right, I'm just going to note this down, so if you go back to this later in your notes, you don't think you're misinterpreting the right-hand rule somehow, right? Why is the force over there? This is what the right-hand rule finds, but it's a negative charge, so the force is going to be there, so of course the magnetic force. Is there also an electric force, like electrostatic force? No, because while there's a current flowing, the wire as a whole is neutral. Right, there's as many protons as electrons, it's just only one of them are moving. But the electrostatic force doesn't depend on whether or not something is moving. Right, so the wire is overall neutral, it just carries a current. Okay, so we figured that one out. So let's now, this is actually what I just told you, right? That if there's a current up, that's really just lots of positive charges moving up, even though realistically we know it's lots of negative charges moving down. Now, if you treat your wire actually as positive charges moving up, and you use the Biot-Savart law, remember that was the law that described how an individually moving charge creates a magnetic field, not a current, right? Not a continuous current. But if you pretend your wire is actually made up of lots of positive charges moving up or negative charges moving down, you're gonna get the same sort of result, right? So the field due to a wire is really just a result of lots of Biot-Savart law applications. We sort of talked about it already. This is a reminder of it. Now, a wire, right, is a bunch of moving charges. A current, rather, in a wire is a bunch of moving charges. So, if a single charge is affected by a current nearby, then each single charge in a wire, let's imagine a second wire up here, instead of just a single charge, each charge in that wire that's moving gets affected. Now again, you can check that a charge times the velocity is going to give you it's the same as a current times the length of the wire. It's sort of like coulombs times meters per second is coulombs per second times meters. If you think about it more carefully, you could justify this more. I'm not going to do it. You can think about tracking a sort of small volume of charges and imagine you move this to actually justify that it's true in full. So what that implies is that my QV cross B, right, that was my Lorentz force law, the magnetic part of Lorentz force law, can be rewritten for a wire and a continuous current like this. Now I put here the arrow over the current because, you know, the current has a direction and a magnitude. Sometimes you can draw the arrow over the L to say, look, the wire has a direction and a length. It's sort of like, it doesn't really matter because either you think of the length of wire being just a length and the current goes in a direction, so it's a vector, or you can think of a current flowing and the wire pointing into the direction. So it's sort of both right. Doesn't matter which one you treat as a vector and which is a scalar. But the point is this, right, is equal to this, so I can put this in for this, and this gives me the force on a segment of wire that is length L. And just as a reminder again, you can rewrite that in terms of the magnitudes and the angle in the way that we've dealt with cross products. Let's do some examples on that. These are some examples. So let's pretend I have a wire inside a magnetic field. So the magnetic field here is created by some other thing, right? By some other set of wires somewhere. This magnetic field here is not created by this wire, right? It's created by something else. This wire would not create a field like this. The wire would create a field that curves around it according to the curly rule, right? It would sort of go, this wire would create a field kind of curves around the back, comes out the front like this. Back, front. Right? Check that that makes sense to you. But we're going to place this wire with that current in a magnetic field that points straight down. Well, what does the force law for wire say? The one we just had on the previous page down here in the corner. I cross B. I is down. B is down. Well, they're in the same direction. I is parallel to B, right? In this example. So that implies that I cross B is 0. Remember cross product? If the direction of the two vectors is the same, the cross product gives you 0, because the sign of the angle between them is the sign of 0, which is 0. So there's 0 force. 0 force on the wire in this example here. So let's then turn our wire around. Let's say the magnetic field still points down, but I'm going to run my current to the right. And of course, it doesn't literally have to be a wire. It could also just be a beam of particles, like you're shooting some electrons. But if they're inside a wire, then we get a forces on the wire itself rather than just on individual particles. Let's apply our law here. So I cross B, so I is the thumb, B is the index finger. I feel like I've done them all the wrong way around. Let me turn this way around just to make my life a little bit easier. Thumb this way, index finger this way, right? So my middle finger, here it is, has to point into the page. Of course, if I turn this whole thing so it becomes awkward with my wrist, the way I'm sitting at my desk, that doesn't change the way the middle finger points. I cross B, I, B, answer down. So the force is into the page. So if this were the setup, the force on the wire would be like trying to push into the paper, like into the table, the desk. Okay, so now let's look at some examples where we actually ask where's the field coming from. So let's look at the two examples here on the left and the right. This is meant to be a separation between the two. Let's look at the case on the left. I imagine I've got two wires with currents, but the currents are the same, like the same in magnitude, or whether one is 1 amp and 2 amps, I don't really care right now. I only care about the direction. If I draw this, say, looking at it from this view here, if this is like my eyeball, right, I'm looking at it from this direction, I'd see two currents coming towards me. Remember, the way to draw this is kind of the same way we draw magnetic fields if they come towards us, except with a circle around it. So we can use either one, right? This one is going to, let me make this one blue, and the blue one, the blue wire, is going to create a current, right? Curly hand rule, current this way, hand curls into the page over here and out of the page over here. Of course, this goes further away too, but I'm just going to draw it here to keep my diagram clean. So that means, could I get a force on this one, or is the force 0? Well, the magnetic field here points into the page, and the current points this way. So this way, current field into the page, that means the force on the wire is towards the other wire, right? We turn it a bit, so I'm not going to break my wrist in the process. Current this way, magnetic field down, force, my middle finger must be towards the other wire. Right? So this one has a force this way. Now, why did I pick this wire? Could I have picked the other wire? Well, let's see what happens. If I pick this wire, let me make it green, it of course also creates a magnetic field. And I'm going to apply the same curly hand rule, and I'm going to get that this one creates a magnetic field that comes out of the page on this side, and a magnetic field that points into the page on the other side. I mean, it looks identical to this one, just shifted down because it's the same setup, right? Like, current goes the same direction as before. So that means the blue wire, right, is sitting in a magnetic field created by the green wire, and the current goes this way. The magnetic field points up because the dots, right? Dots means coming out of the page. This wire creates a magnetic field coming out of the page over here. So if I do this, and it's hard to do, then my middle finger is going to point towards this wire here. Again, you should test that yourself, so it experiences a force the other way. That is good, because magnetic fields or not, any force needs to have an equal and opposite reaction force acting on the objects interacting with. And fundamentally, this is an interaction between two wires, even if we work out what it is via the electric field. So that is good. Our right-hand rules, the curly hand, this one together, they are consistent with Newton's third law. Make a note of this. Right, so what you learned before still applies. Now let me just draw the magnetic field here, because I want to show you a little sort of visualization of the attraction between them in just a second. So the blue one, this is my blue one. Right, this one, it creates a field coming out here, curling around this way, right? Current comes out, the curl is counterclockwise, like this. This one, while it's also coming out, so it's going to create the same kind of magnetic field. And now, of course, there's only one magnetic field, right? It's just in the middle they add up. So in the middle, what you see is here, they sort of go in opposite directions. So the green one goes this way, the blue one goes this way. They're going to cancel out. And the way to sort of visualize this, you can kind of imagine that those lines, they kind of want to then join up and go like this instead. It gives you a fair view of the field, right? It kind of, the circles, this one here, it comes here, it can't go there, there's zero field, so it goes this way and becomes this line instead. So if you actually draw this, you're going to get a magnetic field that looks something like this. And you can check it mathematically if you just add the individual fields, the calculation, taking into account the directions, of course. Now, the way you can sort of see them, they should be attracting is almost like, you can imagine those magnetic field lines kind of like rubber bands. They sort of want to contract. They want to push those, the rubber band is wrapped around it. They want to sort of push them together. Maybe that confuses you, in which case don't think about it again, but maybe it helps you in a way. Remember, if you see this kind of setup, do they attract or not? You can think of these magnetic field lines that go all the way around as wanting to contract. Let's look at the other example where the current go in opposite directions. I'm only going to do one case here, so I'm not going to do the Newton's third law confirmation. You can do that yourself. This is the blue one. The current is the same as before, right? The same as it was over here, so I don't have to think about this much. So now the current in this one goes this way. The field points down, right? Crosses the field, magnetic field due to this one, but at the point where this wire is located, points down. And so my middle finger, you can't see it, it's hidden behind my wrist. Points in the bottom right on the screen. The force here is pointing this way on the wire. And you can check that the force has to point the other way on this one if you figure out what's the magnetic field due to this one at the point where this wire is sitting, right? So you always apply the right-hand rule twice. Once to figure out the direction of the field, and if it's a continuous current, we use the curly right-hand rule. If it were a single particle moving, we use this right-hand, the vector product right-hand rule. But in the second application of it is to figure out the direction of the force, right? So we've got the field, we've got the current, we've got the force. Alright, let's draw this down here as well. And again, I'm going to pretend this is the blue one. So this one looks the same as before. This one goes this way around. And then the other one, now here I've got a current that goes down, right? Down into the plate's thumb, down. So my fingers curl clockwise. Again, you should do that yourself, right? It's hard to show on camera. You should do it yourself. And make sure you use your right hand. I once stood before a class. I couldn't figure out why I was getting the wrong answer to the problem. And it was because I used my left hand to apply the right-hand rule. It does not work. Our hands are not identical. They have different parity. It's a technical term for different handedness. Alright, now what you notice about those ones, right, is that they can't connect. I can't draw a line that goes here, like this one goes this way. This one can't go over here because then it'd be going the wrong way if this one sort of hopped over to do this, like the same way that we had over here. But this one can't sort of go over here and become one line like this, like a sort of looking through a binocular shape, if you know what I mean, because the lines would be in opposite directions. So you can't connect them up like that. But they still can't cross. They sort of get squished in between, right? They have to get squished. If you imagine those lines, they're looking for space. So the way they get space is they push each other apart. Again, it's not what they literally do. Literally, there's a force on the wire, right? We worked it out. But it's a way that might help you, if this thinking makes sense to you, it might help you to figure out which way the force is between two wires that carry currents. Of course, we could look at more examples where the wires themselves are not parallel to each other, right? It could be sort of weird angles, all sorts of directions in 3D space. But you can think about some of those scenarios. Like what happens if you've got a wire that runs like this, the second wire that comes out like this? Do you get a force? If so, in which direction. You can figure that one out. Let's just run through two more examples. So let's imagine I've got two particles passing each other. And pretend it's two positive charges here, and they're going in opposite directions. I call them Q1 and Q2, and they're going with velocities V1 and V2. Maybe they're the same, like two protons. Maybe not. Maybe we've got the same velocity, maybe not. I'm not going to care about the magnitude here, I'm just going to care about the direction. So, much like in the case of the wire, I can start with either one and calculate what's the magnetic field created by the charge. So I might say, what's the magnetic field created by the top charge? And specifically, I'm asking, what is the magnetic field created by the top charge at the point where the bottom charge is right now? And then I ask, what is the effect of that field on the bottom charge? It's going to get me a force on that bottom charge. Now, I can go the other way. I can start with this one and ask, what magnetic field is this charge creating? Specifically, what magnetic field is it creating up where that charge is? And then, what force is that creating on that? And of course, the answers that we get in each case, those two answers should be consistent with applying Newton's third law, namely that the forces should be equal in magnitude and opposite in direction. So, because it's a single particle, we're going to apply the Biot-Savart law. Write this down. To find B field due to the other charge, due to one charge, and then find the force due to that field on the other charge. Now, I let you do this. Remember the Biot-Savart law is the velocity and the direction of r. So if I want to do this one as my, this was my like the blue charge that I'm doing this to, then I take this as my r vector, right, in the Biot-Savart application. So I get velocity out of the magnetic field here is going to be down. This one's creating magnetic field that points down and where this charge is located. So I might draw it like this. I could draw it around everywhere, but specifically here it's down. And then you can check, okay, velocity this way, field points down, the force on the second charge is down here. Make sure you can do that yourself. Like, make sure you can apply the right hand rule twice, once to find the magnetic field due to this one at this point, and then find a force on this one due to that magnetic field. Always this two-step process. Of course, you can double check that there's going to be a corresponding force this way. And I should write this is the magnetic force. Because, well, there's also an electrostatic force. And because they're both positive charges, in this case, they'll actually also repel each other. I don't know which one is stronger, right? Electrostatic or magnetic. It depends on the velocity. Right? The charge features in both, but the velocity only features in the magnetic force. If you're moving faster, the magnetic force might be the stronger one. If you're moving more slowly, then the electrostatic force might dominate the electric. Of course, in many examples that we're doing, you might only worry about the one, but physically they're both going to be there, right? You've got two charged particles. We know about the electric forces between them, Coulomb's law, but also there's a magnetic force that we calculate using the Biot-Savart law and the Lorentz force law. Right, maybe I should add that. Of course, this is the Lorentz force law, which also includes the green part. If you go back to our very first page, namely right here, right, the electrostatic part and the magnetic part. Let me do one more example. There's really one application here, and that's the path a particle will follow if you put it in a uniform magnetic field. And I'm going to visualize this here in having the magnetic field point straight down, right? And my velocity initially is in this direction. Velocity this way, right? Thumb is the velocity. Field points down, so the force is going to be down to the left, like this way, 90 degrees to the velocity. And the force is going to be Q times V times B. And the angle between the velocity and the magnetic field is 90 degrees, so the sine part is just 1. Don't have to write it down. So that means the particle is going to experience an acceleration. A. And I'm just writing on the magnitude. I'm not putting an arrow on top, right? So this is just multiplying the magnitudes. A is F over M, which is QVB over M. So what does that mean? The acceleration is perpendicular to the velocity. Now you remember, hopefully, from your course on in kinematics at the beginning of Phys 161 or 114 or whatever you took, you remember that if the acceleration is perpendicular to the velocity, so A perpendicular to the velocity, that implies it's constant speed and only changing direction. To make it the acceleration, make it speed up or slow down, it would have to have a forward or backwards component. Now that means a little bit later, right? The particle it's sort of going to experience acceleration this way. So you might sort of find it somewhere over here, and then it would be going in this direction. If it's now going in this direction with the same speed, it's going to experience a force that's down by the same logic, right? Thumb, field down, force, field into page, force downwards on page. So that means it's going to have an acceleration down and the velocity to the right. So you're going to find it a little bit later, maybe somewhere over here. Now here it might be going this direction, so its force would be in this direction. Now you can see what's going to happen. The path that this particle is going to follow is going to be a circle. Because the whole time the acceleration is perpendicular to the velocity. Because the force is perpendicular to the velocity. Because that's how the cross product works. How big is the circle? Well, we can do the math here, right? We can say that A is what? It's V squared over R, right? Because it's circular motion. Centripetal acceleration. And that is equal to, we know it's equal to this. Q, V, B over M. We can simplify this a little bit, right? We can cancel one of the V's, and then what do we get? We get that V over R is QB over M. So speed over radius is charge times magnetic field strength divided by the mass of the particle. Right? M in F equals ma is the mass of the particle. So I can rearrange that. Let's imagine I can measure something. It can be arranged if I want to as Q over M. Those are the things that depend on the particle that I'm using, is equal to V over B times R. Right. Now what's the point of this little algebra exercise? The point is that if you have a bunch of different particles, like different atoms, different molecules, different fundamental particles that you don't understand what they are, then you shoot them through a magnetic field, and you can measure, and you shoot them with a speed v that you decide. You set the magnetic field to be what you want it to be, you measure R, and you determine this. So you fix V and B, you measure R, and what it gives you is Q over M. You don't know Q, you don't know M, right? If you don't know either one of them, you can't figure out the other. But it gives you the ratio. So you find Q over M, and that quantity has a name. It's not a very imaginative name. It's the charge to mass ratio. So for example, say you've got a bunch of protons and electrons, right? I mean, they're also going to go in opposite directions. Like they're going to have, say, one goes this way, one goes the other way. But just from the radii that you'd measure, because they have the same charge but different masses, they trace out different sizes of circle. Right? A proton would make a much bigger circle, and it makes sense. It's much heavier, but the force on it is the same, right? Charge is the same. So that is a way to measure what types of particles you have. That's a way, say you've got a soup of a bunch of different particles, I want to separate them into individual types, and they're charged, and I can separate them by shooting them into a magnetic field, and they'll all trace out different paths, different sizes of circle. Now, actually, what you might do is you might not let them have a full circle. What you might do is I might shoot a bunch of particles this way. So soup of particles. Then I imagine I have, magnetic field here. It's constant from one place to another. Right, something like this. And I have a wall here with different detectors. And then one particle might do this. Another particle might do this, bigger one. Another particle might go like this, and maybe, if I set this up correctly, might have a detector maybe along here too. And so, depending where the particle hits the wall, it's something you might be able to detect. You can essentially separate those particles. Or maybe you do even smarter, you build a little channel here, the particle flies into, and you have separated your particles. Mass spectroscopy, for example, something you might come across in chemistry, uses that kind of technique. Alright, now we are not done talking about magnetism. I've got some more planned, but this video is already almost 3/4 of an hour long. So I'm going to stop here, and in the final video on my magnetism grand overview, I'm going to talk about some cool stuff, like I've already written down, some cool stuff. That's what I'm going to be talking about next. And this is really some applications of the physics that we've talked about so far. And there's really a lot of really fun things you can do with magnetism. So I'll see you in the next video. Thanks for watching this to the end.